So I'm happy to have Mirco here with us. He's a postdoc at the Technion working with Aviv Tamar. And today he will talk about interpretability with bandits. And let's hear his talk.
Great. Thank you for the introduction, Michele, and for inviting me, both you, Michele, and Tim. I'm very happy to present this work at this seminar today on classification view on meta learning bandits, which is joined with John Yule, Shai, and Aviv. I'm happy to present it at the interpretability seminar, and you may not understand why by looking only at the title. So I added a subtitle that is a little bit more uh, clear on why it makes sense. Here we want to really to try to understand whether we have a recipe for efficient and interpretable exploration in contextual bandits. So, but you can also say instead of contextual bandits, of course, this will be our setting, but it is like for decision making. So, what does it mean, interpretable exploration in the first place, and how to obtain it? So, we start from the very beginning. So, even if you're not familiar with the setting, hopefully it will be clear enough. If there are doubts, questions, feel free to stop me. Also during the talk, I'm happy to take questions. Okay, so let's get started. So the from the very beginning, so bandits. What is this multi-arm bandit setting? So basically, it's a sequential decision-making setting that covers those kind of scenarios. This is very common. Probably everyone had experienced some this kind of like decision-making in their life. So you want to go to a restaurant, there's a place you already know, like the usual place here, and there's a new one. And you want, of course, to make a decision on whether to go to the usual place or the new one, and you want to maximize your like mm, according to your taste, like that to get the best food. Basically, but of course, there's uncertainty. You don't never been to the new one, so how can you like make this decision optimally over time? Maybe you have to try the new one sometime, then understand for yourself what is better for you. And sometimes this problem is called contextual because you also have some context information. In this example, context can be like you look at like reviews from previous customers who dined at the restaurants, and you can see okay what people think of this new place to make a more informed decision. So this would be the setting. Let me go through the notation a little bit. So it's sequential decision making. I mean, there will be multiple decision steps. So we're not making this decision one night to decide where to eat, but we were making it over several nights, and we want to maximize the reward that we're getting over time. And the context will be just a vector of features, so a vector in RD of reals. The dimensional coming from a context distribution that we assume here for the rest of the talk will be fixed, a fixed context distribution. So let's say the user's um, rating of the example will be coming from a fixed distribution. We have our agent that has to take decisions like in the model are not really restaurants, but they're like what we call arms. Arms are decisions that you can take or pull, and these arms are basically probability distributions with some parameters. Theta k will be the vector of parameters of the arm k, also in RD. I'm saying probability distribution over what? Basically, those are distribution over rewards. So rewards, we assume they're stochastic and they're coming from distribution parameterized by theta. In this talk, we consider linear contextual bandits, which just means that those probability distribution nu for each of those arms. So the probability on of the distributions of rewards that we're getting when the context is X and the chosen arm is K is linear in the context features and the parameters of the arm, plus some random independent noise, typically Gaussian. Last thing we have to introduce is the agent. The agent will be represented by what we call a decision policy. Decision policy get to see the context, like remember the reviews in the restaurant example. And you see the policy is like as an index T because we can first of all change at every step, and the policy can see what happens in the past. And the policy is a function from this context to the decision at this step. And the decision will be between 1 or k. This is like a set of these discrete terms that we consider discrete in this setting. So just to give, aside from the restaurant examples, more like this is actually a model that's being used, like people say at least, like, sometimes it's not public, that is actually used in production, linear contextual bandits or contextual bandits. So let's consider more like real world applications. The context, this is movies recommender system application. For instance, the context may be user features. So you see previous movies that the users have like watched or rated. And we want to recommend to this user the best movie for tonight. So the arms that we can take with our recommendation policy will be movies. And the reward will be the actual user rating for this movie. Another word application can be healthcare treatment. Now, the context is like patient features. So, let's say medical history of this patient, age, gender, those kind of anagrammatic features. We want to provide to the patient the best treatment for their case. And so the arm is a treatment. We have a set of options we may want to take the treatment from. And the reward in this case would be the response to treatment of the patient. We want to improve the condition of the patient. And so the reward will be high when the patient's condition improves. So this is the setting with the notation. And there's one last thing, like we said, yeah, we want to maximize a reward over time. What does this mean formally? So there's another object I need to introduce. It is called the regret. It is a little bit, it is mostly for theory, but let me first explain what it is. So we fix a number of rounds. So these steps will be from 1 to h in this case. And we want to understand the regret of taking decision with a fixed with a particular policy, and the regret will be the reward that we get at the step T. Sorry, the optimal reward that we can get at the step T, which is this one. So we maximize over K over the arms. At basically the expectation of this distribution here with respect to what our policy is choosing. So if our policy is always optimal, the regret will be 0, and we compute the regret not on the a specific instance here, but over the worst case instance. Where the worst case, it means like the most like challenging instance for a given algorithm or policy. So we can make example for the regret too. Typically, you don't have the regret in the real world. You may be able to compute it in hindsight, but why you don't have it? Because like for the movie recommendations, the regret would be, let's say, the rating of the best movie to recommend to this user minus the rating of the recommended movie. But typically, if you recommend one movie, you don't see the user rating also for other movies that you didn't recommend, so you don't know which one was the best movie or the best treatment for the patient. You know the effect of the treatment that you are administering, but not other treatments. Okay, so this is like the setting. This is probably the slide with most notation. Now I want to take for a little bit the healthcare example and dive a little bit into it.
Mirko, can I ask a question?
Yes.
So sorry about the definition of the regret. It depends on a policy pi that's
Mhm.
entering in the expectation, but what is the expectation over there?
Okay, the expectation is over the all of the realizations. So the point is that the policy depends on the realizations in the past, and this RT is stochastic, coming from this distribution. The only without the expectation, like of course there are other definitions that regret without the expectation if you want to be robust or percentile or something. But this means like I don't want to counter regret if I'm being very unlucky.
Oh, this is the policy of the learner, the pi.
The pi is the policy of the learner.
Oh,
Yes.
yes, I see. Okay, thank you. Yeah.
And this with the max, you can think of it as the best policies that you have in the problem.
Yeah, no,
Okay.
I thought it was the policy you were comparing to, so that's how I got confused. Sorry.
Oh, right, right. Okay, okay. Sorry. No, it's not the comparator, but it's the policy you're using, and this is like the comparator. Okay.
Thanks.
Thanks for sort of like confusion. So I was saying, yeah, healthcare application. Let's take a fixed patient here. So the context that typically in contextual bandit changes at every step here will be fixed for the next few slides. We want to see what are the bandit approach to this problem, like diagnose this condition of the patient and give the best treatment. So typically bandit approaches are like optimal exploration exploitation. And I will say what does it mean? Optimal through two like groups of algorithms, usually optimistic algorithms or like Bayesian inspired approaches. So for optimism, probably the most famous algorithm is UCB, stands for upper confidence bound. How does it work? It's very simple. Like we have set of arms with their rewards. For every arm, we keep track of an empirical average of previous rewards that we got by administering those treatments, and also a confidence bound around it. And the algorithm doesn't pick the arm with the highest like average reward so far, but the one that has more potential, so the highest upper confidence bound. So in this example here, it would pick this arm, and you will get a realization. So what happens given this particular treatment? And since the realization is quite bad, you can improve the confidence bound, and maybe the confidence bound will be a little bit lower. So now you will choose another treatment. This is a very efficient algorithm theory. Indeed, this is the regret that has been proved for UCB. So it depends on the number of arms and the square root of the number of rounds, a number of round decision. So it is for sublinear. And also, it has been derived also lower bound that says that this algorithm for this measure of regret in the worst case cannot be improved up to like constant factors. And in this way, it is optimal in the exploration because like it's like it matches the theoretical lower bound. This is for optimism. Bayesian approaches instead. Bayesian inspired the most famous, say, Thompson sampling. Same graph, arms and rewards. Here I'm Thompson sampling. Like you start with a prior, and you try to model all of the distributions of rewards for every arm. Let's say here the prior is that the rewards are Bernoulli distributed by a Bernoulli with parameter 0.5. What do you do in Thompson sampling? You sample from all of this distribution for all of the arms. Basically, this is what you can get, some 0 and some 1. And then you will pull an arm for which you got in these, let's say, synthetic samples from which you got the highest reward. Let's say this one, because this one you break time some way, and let's say you select this one, and then you see the rewards that are actually coming from the real environment, the real patient, not the one you're according to your model, but from the real distribution for reward distribution for this arm. And then you can update your prior into posterior, where, of course, here the treatment resulted in a bad reward. So you update the prior downward. Then you do it again, and maybe you will choose some other action. This is also has been proved to be optimal, matches the theoretical lower bound up to constant factors, and it is also very efficient in practice. We will see a little bit that also in very last slides with some numerical validation. Some are very strong baseline in practice too. And so those are the bottom line for the bandit approach. So the one coming from, like, say, reinforcement learning people is a CB and Thompson sampling, very efficient in theory, but are they interpretable? Hard to tell, but I don't think they're very interpretable, because you don't really, it's very hard to predict what will happen using UCB and Thompson sampling without knowing the realization. So, of course, if you know the realization, you know exactly what will happen. You can write down the trajectory that you will get, but without the realization, is very hard to do. I will tell you later why I think this makes these algorithms not interpretable according to a more like formal definition. But I'm also putting here the question mark, because as you will notice, I'm not an expert in interpretability. So, like, if you have, like, for every of those claims, if you have, like, doubts there, they make sense, feel free to tell me. It's true. It is also intended as a learning experience for us that are not coming from interpretability. Let's look at what is the human approach instead. So maybe you can learn what does it mean to be interpretable by looking at what humans do. So for this diagnose and treat, I think coarsely the human would proceed this way. So you have a task, like in this case, to administer treatment. You acquire knowledge from sources, let's say historical data, science, of course. From medicine, you have some, like, a strong prior on what will happen administering treatments. You get some experts to design a standard strategy. Once the strategy is designed, physicians can just, like, load it or look at it in a book and can follow the standard strategy. This is an example, a real-world example for asthma diagnosis and treatment that is coming from the global initiative for asthma. And you see, like, it's very easy to follow. Indeed, we believe it. This is actually very interpretable. We're not physicians ourselves, but you can still understand what is this about. Are the symptoms typical of asthma? Yes or no? You follow basically a decision tree, or represented in this flow chart. But is this efficient? I doubt it is, for a very specific point, that this is a standard strategy that has to work for every patient, basically. So it has to be very general, but is it the most efficient strategy for a specific patient? Maybe no. We don't know, but maybe no. So let's try, let's assume it is not the most efficient strategy. Can we use, like, AI to take the best of both worlds? So we would like a strategy that is as interpretable as human strategies, but also efficient, or perhaps efficient like a bandit strategy, which are, like, theoretically optimal. So this is, like, the question, like the quest that I would like to answer in this talk, giving our take on how we think we could do it. I will start with a brief problem setting and then presenting the algorithm. The problem setting will be a little bit different than what I presented you before, but on the same beats. We'll provide some theory and numerical validation, and then that will be it. So, okay, interpretable and efficient exploration in contextual bandits. Let us start from a tweak of the setting. So I presented you contextual bandits with the restaurant example, but here is a little bit different. It is a meta learning setting. Why that? We like this setting also because it is more closer, in our opinion, to the healthcare example that I was telling you before. Because like in healthcare, you may assume that you can have data of a lot of patients in the past, that you administered a lot of treatments to different patients, and you, let's say, track down what happened. So the idea is that maybe you can take a class of bandits, not just one, as before, with a fixed context distributions. Each of these bandits is exactly what I explained you before, so a linear contextual bandit. But now we have a meta training phase where we can just interact with all of these bandits at will. So a lot of historical data, simulator, those kind of settings. And what we want to do is to extract from this meta training what we call an exploration plan. So a decision policy that starts from the very beginning, step one, and goes to step H and takes like trajectories, so like of realizations, and decides what decision to take in the next step. Why we want this exploration plan? Because we will have a test. So we want to extract this exploration plan, but at some point we will have a test bandit. So a patient in the future. This could be, of course, in practice, a new patient. Here we assume the patient is coming from this class, because maybe this class is not the class of patients, but like patients types. So you can imagine like the future patient coming from one of the types you already have seen. Same context distribution you had at meta training. And here we want to minimize the regret. While meta training happens most of the times offline or like on simulation, the test happens in the real world with a real patient. So we want to be really efficient in the decision. We want to minimize the regret. We don't want the patient to take bad treatments. We want to quickly understand what is the best treatment for the patient, and we want to use this exploration plan that we have extracted. Of course, there's the standard way to extract exploration plans, which is like UCB and Thompson sampling. You see here a letter and that like the notes that these are the same algorithms I presented you before, but with some adaptation to the meta learning setting, but they're otherwise very similar. But the point is, can we do it can we take interpretable plans? Can we design from this meta training interpretable plans? So what does it mean for an exploration plan to be interpretable? So we're not coming from interpretability expertise ourselves. So like we try to be conservative. So let's say what the humans do is interpretable, or we believe it is interpretable, because like human design them to be to in a way that they can understand at least, and other people can understand most of the time. Those standards are like designed for other people to use. So let's try to take this real world example and translate it to how it would look in a bandit setting. So here you see like a question: are the symptoms typical of asthma? In bandits, you don't ask question, you can only pull arms. So let's say this question is like represented by one arm. It is one decision of the bandit problem. And it can be arm 3. So in the bandit, you will have choose arm 3. Typically, those questions are all like one step. So you take this decision once and you see the results. In bandit, typically you have to take to pull an arm more time to conclude anything that is like statistically significant, because the rewards are stochastic in the general case. And so if you don't pull multiple times, you don't have like a robust estimation. And then you would like to say yes or no. In bandits, you don't have yes or no as well. You just have rewards. So instead of the yes or no, you may have the average reward that you're getting from pulling this arm free n times. And instead of the yes or no, you could design this like the split as is the average reward that I'm collecting lower than 0.3 or larger than 0.3. And then I can go on the flowchart to define the subsequent steps. So our conjecture is that this exploration plan on the right-hand side is interpretable because it looks exactly like the human strategy. So we try to mimic the interpretability of this human strategy in a bandit setting. So we want an algorithm that interact with offline data or simulators at meta training and produces something like this. How can we do it? So here you have our solution to that problem, which we call explicit classified and exploit. It will be clear in a moment why. So basically, we want to produce this decision tree on the right-hand side. Of course, we want to understand which arm we have to take here, if it is 3 or 1, at those thresholds, the number of rounds we have to take, and we want to do it like automatically with a meta training algorithm that takes samples from the tasks, let's say offline on simulation or from historical data. So how does it work? We have a decision tree. We start with all of the candidate bandits. Like let's say we consider at first it can be any patient type. Then we make a test over the bandits, which is like the question I was like telling you before for the asthma. Is like I want to test the average reward. New case, the average of actually here the expectation of the rewards for a given context collected with arm K. And they want to test whether this expectation is lower than B, which is a threshold. And assuming here that the rewards are between 0 and 1, so the expectation will also be between 0 and 1. So this is a test. And then we will have like an answer to this test. So basically, yes, it is on the bandit I'm interacting with, the expectation of the rewards of this arm is smaller than B. So I will go to this side. If not, I will go to the other side. So decision tree, I can go ahead until I have leave nodes where I have just one bandit, and I can follow the decision. And if I get to this node, then I classify this bandit instance as mu4. So mu4 would be a bandit instance for which this test is yes, this is no, and this is yes again. Well, does the algorithm do those? Because the point is that we don't know which test to make. So what has this K be? Like I'm calling in mu K in all of the branches, but those are different Ks in principle, and also B are different. So those are different tests that we have to design. So our algorithm want to design those tests, and you want to do it by keeping the depth of the tree small. And especially here, I would like to do it keeping the depth of the tree the optimal depth. So the smallest depth given the problem and the set of tests I can choose. So the set of arms I can pull. So I want to do this because I know that I can, this is bounded. Even in the worst case, this will be smaller than the number of bandits I have, like 5 here minus 1. Because in the worst case, of course, you're like, with every test, you're like, eliminating only one candidate. This is the worst case, to have this worst case step. But fortunately, we cannot design an algorithm that does that, or an algorithm that does that efficiently, because there's a traditional result that says this computational problem of designing those tests for the optimal depth is NP hard. So it's we don't have an algorithm that computes them in polynomial time. So let us do this optimal tree here on the right for a moment, because it's like it's a ideal tree, but it is a pipe dream. So what can we do instead? Instead of taking optimal splits, we can design one test at a time and take the greedy test. So I don't know how to design the tests altogether, but I can design the optimal test here according to some criteria. And here the criteria would be, I want to maximize the entropy of the split. What does it mean? Simply, I want to have a lot of bandits, same amount of bandits on the left and the right, right? Because so I'm like collecting a lot of information from this test. This is why it is greedy, because I can eliminate 2 candidate bandits, or in this case, or a 3 if the answer is no. So I'm acquiring a lot of information in one step. Our algorithm does that. So compute the, and it is a tractable algorithm, so you can implement it and running, and you can run it in polynomial time to get a tree. This tree has the same depth of this optimal tree, but this is not guaranteed. This is just a small and dumb example, but this is not guaranteed in general. Because we're taking greedy steps, those might be suboptimal, but we have like a theoretical way to bound this suboptimality. And this suboptimality is given here, just a second. So we can show that by taking this greedy test instead of the optimal one, our depth will be larger than the optimal one only by a logarithmic factor of the number of bandits. Also traditional result. So we got from our algorithm, meta training, pretty simple. We got an exploration plan that is small enough. And this, why I'm saying is small enough, because of course, like one thing I didn't, it's the right time to mention, I think, is that of course I'm building a decision tree, which can be used at test time. I will show you why in a few seconds, but I can build a decision tree maybe also for the UCB and Thompson sampling algorithm. So you're saying you're building a decision tree, but this is just a representation of an algorithm, but maybe I can represent it with a decision tree, Thompson sampling and UCB as well. And that is true, you can. But what you cannot do, and we can do instead, is that you cannot bound the depth of the decision tree that is coming from UCB and Thompson sampling, because like in the worst case, their depth will be the number of rounds that I'm taking, because like they are heavily dependent on the realizations. And so in principle, you don't have this result on the bound on the depth. And we believe that this is very important. This is what makes actually the algorithm interpretable in our view. So this is not the full picture, though. We got this exploration plan. How does it work in practice? So it's very simple. Let me put the exploration plan aside. This can be seen as like the standard strategy, for asthma. You can print it out on a page. In this case, it's very small, but like let's say in a book, and you can read it when you're interacting with a test bandit. So we're taking a new patient, for which we assume the patient type is something that we already have seen in the past in the meta training. Now we want to understand which this patient, to which type it corresponds. We don't know whether I is 1, 2, 3, 4, or 5. So we start following the strategy. So we look at the tree here. We look at the K here that we have to put and the B. And what we do is that, okay, we take this test. We collect N samples in this way. We sample context from the context distribution, which is fixed again, the same as meta training. And we collect rewards. We collect empirical rewards, so we can estimate mu k. So let's say average of the rewards we collected, and then we can test whether the mu k we obtain. Let's say this. You can think this is not the mu k you find here. This is a empirical mu k, so the average. If it is smaller or larger than the threshold, let's say it is not. So it is not, I can look at the exploration plan again, and now I have to test another mu k. So I will do the same for another mu k. Maybe the answer this time, I collect and sample, and the answer is yes, and I obtain mu 5. It's a leaf in the exploration plan. This means that the exploration for our plan ended here because we classified this test task, which is unknown. We don't see the patient type when the patient comes, as mu 5. And now we can just play decisions, assuming that this test task is mu 5. So the patient type is mu 5. So we will collect other contexts. We will always take the optimal arm for mu 5, which is the K that maximizes the expected reward for mu 5 for all of the remaining steps. So here we spent a few steps on the tree, and now we identify the task, and we can just play the optimal strategy for mu 5. What can I think it's pretty easy to understand how it works, but what can go wrong here? So of course, what can go wrong is that these mu k are averages here on the test task. So I may fail a test. Like I may say, okay, for me, the result of this test is no, but instead it is actually the ground truth is yes. And how can I avoid it with enough confidence? Basically, I have to design N, the samples I'm taking for every test, in a way that I can be confident about the answer of the test. And let us look how to design N. So basically, what is the problem with those tests? Why they may be hard? Because maybe we have we designed the threshold in this greedy way, but maybe we have two different tasks. So two different mu, J and I here, for which this arm K, the reward distributions are very similar. And so their mean, their expectation of the reward, mu ik and mu jk, are very similar and maybe also very close to B. So maybe I'm taking sample from mu jk, but the answer of the test here is no, because I'm making an estimation error, of course, because those mu here are estimated. But of course, I can assume, like, this is like a critical problem. I want to design n, the number of samples, in a way that is robust to these like bad cases. So basically, take a separation parameter, which we assume known here, but you can also learn it, extract it at meta training if you have enough data. So the separation parameter basically says that for every pair of bandits or patient types, in the class, we have at least one arm, a one arm, a K. Here K is not fixed, for which these two patients are different enough. So it means that basically, like, there aren't two arms that are for which the difference is so fine that so small that I can't really understand which one of the two I'm interacting with at test time. So with this separation parameter, what we will do is like design n so that is like a constant divided by lambda, so that if the tasks are not well separated, I will need a lot of samples to take for my tests. When a lambda is instead large, so tasks are well separated, I will need less samples. So some theoretical guarantees of this simple procedure that I showed you is that under the separation assumption, we can prove the regret of this ECE algorithm, the one I just showed you, and we can show that the regret has this expression. Let me unpack it for you, because there's a little bit more of notation. So I recall that this C star is the depth of the optimal tree for this setting, and lambda squared is the separation that you find here. H is the number of rounds for the regret. M is the size of the class of bandits here. So we can see that the regret looks pretty good, because it's basically dominant factors are these C star and lambda squared, and we only have a dependence with the number of rounds that is logarithmic. So of course it is sublinear. So it means that our algorithm is the longer H, the less mistakes it will make, and the better will be the regret in cumulative regret. Is this good? So basically, I showed you the lower bound before, but here we are considering a further assumption, so that the arms are separated, an assumption that you usually don't have in the general bandit setting. So we need a new lower bound, but luckily we can show a lower bound that says that, yeah, this strategy is pretty good, because we can prove a lower bound that has mostly the same terms. Not exactly. Here you will see that C is with a tilde, which means that it's mostly a technical artifact, that this C refers to a randomized decision tree, whereas this is a deterministic decision tree. Randomized, I mean, here in the algorithm, I'm taking for every test I'm pulling one arm. And here in the lower bound, you have this C, which is like for a tree that is like a distribution over arms for each test. But we have a way to link the two, and basically you can say that this algorithm is almost matching up to logarithmic factors. So it is pretty efficient. I will not go into the details of the lower bound, because derivations are not that trivial to present, but maybe it's more interesting to show at the hard instance that we use to design this lower bound. Let us take, we can take two bandits, and basically we have to classify whether we are interacting with bandit nu1 or bandit nu2, and those are the rewards distribution. Let's say this is the parameter, those that red dots are parameters of Bernoulli distribution. So of course, the problem is that these bandits, if I want to find the optimal arm, you see that there are two bandits that are two arms that are very close in the reward. So if I keep pulling arm one, there's a huge chance that I will get a good reward, because in both of them, the reward expectation is good. But it's very hard to tell whether I'm pulling arm one in no1 or no2. Instead, if I pull an informative arms, which I'm sure it is suboptimal, because it is suboptimal in both of them, I can collect a lot of information. Like pulling this arm, the reward will probably be quite bad, but you see that there's some separation between the two expectations. So if I pull this arm tree and the reward is like for a couple of times it is 0 or 3 times it's 0, I can probably start thinking that this is the task I'm interacting with, because like here the expected reward is a little bit higher than 0, so I'm not expecting to see 0 over and over again. So this is like the hard instance that you use to construct this lower bound. Now, after theoretical guarantees, we tried our algorithm. Of course, this is what the theory says, but does this algorithm works in practice? Let's say practice here is not really practice, and that means we use like synthetic simulated domains, so not the real world, but we wanted to test whether in those domains our algorithm was like good enough. Why am I saying good enough? Because here we don't really want to beat the baselines, because as the main point of our algorithm is that due to its simplicity, the way it mimics like the standard human strategy on some application, our algorithm is interpretable because I can print it out, giving to experts to read and to vet. And so MUCB and MTS are instead baselines that are not interpretable. Like I can maybe represent them with decision trees, but they may be very, very long. So like a very long book or something that it's very hard to read. But we still want our algorithm not just to be interpretable, but to be efficient. And those are like very efficient baselines, at least theoretically. Here I'm showing 4 different tasks. And just how to read the captions is, first part of the caption is the name of the task. Hard is basically an instance that is like looking like the hard instance we used to design the lower bound. And rand is basically a random instance. So I'm sampling, like I'm fixing the number of tasks of bandits in the class here. So here we're considering an hard instance with 5 bandits and 10 arms for each bandit. Here is the same, but now the bandits are random. So it's like a random set of K distribution, contextual also. And finally, lambda is the parameter. So it says whether the tasks are well separated or not. As you can see from A, for instance, our algorithm, it is actually pretty efficient, not as efficient as Thompson sampling, which is a very efficient algorithm in practice. But as you see, the regret is not far off. And also you see that the regret is collected in a few steps where we have to make our tests. But once the classification is done, then you don't accumulate any more regret. Actually, it is even more efficient than Thompson sampling in understanding what is the task, because you see here, Thompson sampling is still learning a little bit, still like changing the posterior, still trying to get the optimal arm right. Whereas afterwards it gets very good. Whereas UCB, even in this setting that is like just 5 bandits with 10 arms, UCB looks almost linear. Actually, it is not linear. The regret will go down at some point, but it is very slow, very inefficient practice. And these takeaways are consistent across tasks, even if you take a pretty large task, so 40 bandits with 40 arms each. See, our algorithm is still pretty efficient. Thompson sampling is even more efficient, and UCB is a little less efficient because it suffers from say over-exploration. Right? It explores a lot of suboptimal arms. So these are the numerical validations, which are in synthetic domains, but they're encouraging. So we are, of course, planning to test this algorithm in more challenging domains. And why we want to do that? What is the end goal? So as I said at the beginning, this project is like the goal of this project is to try to understand to how to build interpretable and efficient exploration in contextual bandits. Something that we really didn't see studied or definitely not solved in the literature. Our solution is still quite simple. So what we are essentially doing is distilling an optimal exploration. You can think like UCB and Thompson sampling into a decision tree with bounded depth. And this way of saying that this like interpretability, like it's not a definition yet. It's like more what I'm telling you is more informal, but it may resonate with some of you that follow like the Shai Mansur talk in this same seminar few months ago, like a couple of months ago. Shai presented this paper with. Barestan is in the first author, where they were like showing how interpretability can be formalized into a small aggregation of simple hypotheses, where the small aggregation was indeed a decision tree of simple hypotheses, which in their case was like supervised learning, so classification tasks. And in our case, the hypotheses are like tests that we're making in sequential decision making. So we noticed this like definitely this link in the way we were thinking of interpretability coming from human strategies and what they formalized for approximation for interpretability of classifiers. And this is the end of the talk, but I would like to conclude with a let's say a more like open-ended question, especially for the discussion. Like, is this the right way, the right approach for interpretable exploration? Are we getting not a definition, but like a framework for interpretable exploration right here, or sequential decision making is very different than classification, so we should do something different? Are the algorithms that are already known already interpretable because they're theoretically grounded, or this like interpretability is actually a need that practitioners have, and they cannot trust the literature algorithms because they don't understand what they may. Most of the times in practice, what you hear a lot from practitioners is that Thompson sampling and UCB may be simple algorithms, but you need some knowledge of quite intricate like statistical consideration. Even if you have this expertise, it's very dependent on the realizations. Here we have an algorithm that, of course, for simple settings for now, and we may want to scale this up, gives you a decision tree that you can really print and see what it does, and you can decide whether you like this exploration strategy and whether you want to implement it in your application. Of course, it is still a long way, but we really would like to understand, to see what is your opinion on whether this is the right direction. So that's it on my side, and just reporting the references. You have the link of the paper if interested. Thanks a lot for your attention.